Can you see my screen?
Yes, we can.
Okay. Okay, this week we're going to learn the sampling theory, which is one of the most important theory in the signal processing. Okay, the first, let's start with the outline, what we're going to learn today. First of all, we're going to go over the convolution property of the Fourier transform that we learned in the past, including the convolution in time domain, as well as the convolution in the frequency domain. What are the interpretation of these properties and their application to the sampling theorem? So after this introduction, we're gonna go over the sampling theorem and then define what is sampling theorem. You know, what are the restrictions and what are the conditions when you sample a signal, continuous time signal, in order to convert this signal into the digital domain, so that we can process at the CPU or NPU and different kind of processing unit. One of the key process here is called interpolation. So first we sample at the first step to store or to process these signals in digital domain. So after we are done with this processing, how to reconstruct this signal and then convert back to the original format. So we need an interpolation in order to reconstruct a signal from its samples. So what are these process? And then we're going to learn this. Especially, there's a rate called Nyquist rate in the sampling theory. This is very important. So in order to reconstruct a signal from its samples, we need to sample these signals at a specific rate. Otherwise, we may lose this information. But what happens if we sample at a smaller rate than Nyquist rate? What kind of practical problems that we can come across, including aliasing problem, and how do we mitigate or solve this aliasing problem in practice? And the last, we're gonna show you some application of this sampling theorem to process a signal in communication systems, such as Wi-Fi, GPS, and so on. So that's one of the important block in this case is pulse code modulation, PCM. Okay, let's start with the convolution. As you guys see, the convolution in this case, let's say we have two signals in time domain. One of them is G1 of t. The second signal is G2 of t. And the corresponding Fourier transform that we learned, let's assume that is G1 of w, and the other signal corresponding Fourier transform is G2 of w. If we convolve these two signals in time domain, as you can see, the convolution of G1 of t with the G2 of t, this corresponds to the multiplication of this signal in frequency domain. Similarly, if I do the reverse operation in frequency domain, in other words, if I convolve G1 of w with the G2 of w, this is going to correspond to the multiplication of two signals in time domain. And let's remember, guys, what was the definition of the convolution? G of t with the w of t, it was equal to from minus infinity to infinity, g of tau times wt minus tau d tau. That was the definition of the convolution. So Another important concept that we need to learn prior to going to the sampling theorem is called filtering. Filtering, a system, like LTI, linear time invariant filter, as you see in this box, has an input of delta t and output of h of t. So the filter response to this input, which is delta of t in this case, is going to be h of t, which is the impulse response of the system, or the impulse response of the filter. Let's generalize this. For any input x of t, the filter output is going to be, of course, the convolution of the input with the system impulse response. In our case, is filter. So similarly, sampling can be interpreted as a filtering, basically. H of t can be a sampler, is a device that sample your input continuous time signal, and the outputs can be the samples of this signal. So in this case, in time domain, we have an x of t, we have an h of t, and the output is going to be the convolution of x of t with the h of t. Similarly, in frequency domain, the corresponding Fourier transform of input signal is going to be x of f, and the Fourier transform of the impulse response is going to be h of f, which we call channel response or channel transfer function, h of f times x of f. So in short, the output is going to be the convolution of input with the impulse response in time domain, and this is going to correspond to the multiplication of the input with the transfer function in frequency domain. This filtering, as well as the convolution concept, that is going to be useful when we're going to talk about the interpolation and the sampling in the next few slides. Okay, so after these two concepts, which was convolution and the filtering, now we are ready to talk about the sampling theorem. So definition, by the definition, okay, any signal in practice is basically a continuous time analog signal, right? So like the bird's sound, the speech of a human, the video, all these, things are in the practice are continuous and analog signal, right? In order to, record and process this signal, first of all, we need to convert them into the digital samples in the environment that computer can process these samples, right? So this is where the sampling play an important role in this case. Okay, then the question, I have a continuous time signal. How often that I should sample this signal? In what frequency? In what, right? Rate that I should sample this signal, collect the signals from this continuous time analog signal. So technically, what is the condition to sample a signal so that I can later on reconstruct this signal and then, extract this signal? Let's say any signal band is limited to B hertz, bandwidth hertz. Let's call B hertz. A signal has a bandwidth of B hertz. This can be reconstructed exactly without error from its samples if you take a, samples at a rate greater than 2 times of B. So if your sampling rate is greater than 2 times of your signal bandwidth, then you can reconstruct this signal from its samples without error, without loss. In other words, the minimum sampling frequency is called fs is equal to 2 times b, your bandwidth, the bandwidth of your signal. So this is called Nyquist rate. This rate fs is called Nyquist rate. So if you follow this Nyquist rate to sample your analog continuous time signal, then you can reconstruct this later on without error. So let's give an example. So you need to record your speech, for instance. So you have a smartphone or your laptop, doesn't matter. It has a microphone, right? So you talk to the microphone, and this sound wave, they are recorded and then sampled. So if you sample this at a Nyquist rate, then store in your smartphone memory or the laptop or computer memory, then you can later on listen to your speech, right? Your voice. But if you don't sample at the Nyquist rate, then you're gonna store your voice, your speech with some error, with some loss. And when later on, when you try to reconstruct or to listen your voice or speech, you may hear some, the noise or some missed, information. So that's why it's very important to follow up the Nyquist rate when you sample a signal. Okay, what mathematically is going on? How do we define where these 2 times of B equation comes? Let's learn together using the convolution and property that we just introduced. So assume that I have a signal x of t. This can be a speech, it can be a video, or it can be a text. So let's say I have a such continuous time analog signal, and I want to sample this signal so that I can convert into the digital environment. So sampling means actually we have a delta function. You see summation from n, and delta is t minus n times ts. Ts in this case is the sampling duration between these two delta function. So this ts sampling duration, it actually determines the time that you are collecting the sample. Let's say ts is equal to 2 milliseconds. So that means the duration between these two delta function is 2 milliseconds, sorry. That means you are gonna collect every 2 milliseconds the samples from this continuous time signal. So collecting means, or sampling means, we're gonna multiply mathematically x of t with this pulse train. We call actually this pulse train. Each of these is a pulse or delta function. We have a series of these pulse, that's why we call pulse train. So I'm gonna multiply the x of t with this pulse train, and it's gonna be equal to xs of t sampled signal. So as you see, I just collect or record this value, this value, this value. So that is mathematically the sampling. Okay, so multiplication, remember guys, from the convolution property, multiplication in time correspond to the convolution in frequency domain. So this is the interpretation of the sampling theorem in time domain. But let's see what is going on in the frequency domain. So let's show and explain this multiplication in the frequency domain. So the x of t, the Fourier transform of x of t correspond to the x of f. So let's say if you apply a Fourier transform to this time domain signal, I obtain this x of f, which has a bandwidth of b hertz. And then similarly, the convolution of this pulse train is going to be equal to this equation. Again, is another pulse train, but now the duration between two pulses is 1 over Ts. 1 over Ts, actually we call it Fs, remember? And Fs was sampling frequency. So as you guys know, convolution I teach you guys is as you sliding this shape over these pulses. So as you slide this signal, this shape, triangular shape over this pulse train, in other words, if you apply the convolution, this looks like the result. So as if you are sliding this triangle shape over this pulse train, and this is what you end up, which is the replication of this signal bandwidth every Fs, or 1 over Ts. So Fs, Ts, remember guys, and that was B and that was another B, right? So Fs start from here, the next Fs is equal to this, and that was the B, and another B is equal to 2B. So your Fs, your sampling frequency, must be greater than 2B, as you see, one bandwidth from here, another bandwidth from here. So total is 2B. Your sampling frequency minimum must be 2 times of your bandwidth. Otherwise, if it's smaller than that, what's gonna happen? This shape, they're gonna overlap to each other. We're gonna see is gonna create a problem. So that's in one shot is the definition of the sampling theorem mathematically, as well as the visually in time domain and frequency domain. Okay, so let's continue sampling theorem. So by remembering some Fourier transform pair to explain this sampling theory further. So this is my time domain signal f of x. X in this case is time domain. And if you apply the Fourier transform, let's assume that this signal has as such Fourier transform. And then if you want, you can extract or get back the original signal from this signal by applying the inverse Fourier transform, right? So let me give a specific example. This is a cosine signal, as you know. It's one of the most popular function that we use, signal that we use in practice. So this is my cosine signal. And if I apply the Fourier transform, I teach you guys that the corresponding is going to be 2 delta function. One of them is on the positive side, the other on the negative frequency side. So the Fourier transform of a cosine signal is equal to this 2 delta function, or impulse function, we call it. Similarly, if I have a pulse train in time domain that I just show you, with separated by W, right? Or in this case is Ts If I apply the Fourier transform, again, this is gonna be equal to another pulse train in the frequency domain with duration of minus 2 pi over W. Okay. So, convolution of a signal with a pulse train. That was the sampling, remember? That was the sampling in the frequency domain. Interpretation of this sampling in the frequency domain. So this is my signal in time domain, right? And then if I convolve this signal with a pulse train, as I told you guys, I'm just not, what I'm doing is actually I'm replicating, I'm making a copy next to each other. But when I make a copy, as you see, each of these has some side lobes, right? Side lobes. So these side lobes may overlap to each other, as you see from here. So these side lobes is actually including some of your information, which is a voice, video, text, whatever. So you need to be careful to protect this side lobe as well. So information, of course, most of the information in this main lobe in this center, but still there are some information on the edge side, on the side lobes. So when I sample a signal, I'm copying your information, my information, every fs, which is sampling frequency. Okay, so how to sample a continuous time signal? That was my original time domain signal, which can be your voice or bird signal or some, continuous analog signal that you collect from the real environment. And I need to sample this continuous time signal so that I can process or store in a memory or in a CPU. So that's what I said. I'm gonna multiply this signal with the pulse train, right, in the time domain. That was the sampling. So if I sample this, actually, I'm just collecting the sample, the value every TS, which is this. So the shape is gonna be this from this point, and the second value is this, and the third value is this, fourth value is this, and so on. This is gonna be my sample signal in time domain. Okay, so now we came to the most important question. I'm gonna sample my continuous time signal, but at what rate? How often? Every how many second or millisecond I should collect the samples from a continuous time signal? Okay, so that was my original time domain signal that I recorded. I need to sample this signal with this continuous time with the pulse train, right? So let's say the Fourier transform of this signal, it has a such result, such shape. The Fourier transform of this signal has this result, has this shape. So when I multiply this signal with the pulse train, actually, I am copying this, replicating this signal every fs sampling frequency. So that's when you record and when you convert an analog signal into the digital. In other words, when you sample a signal. So I sample this, I store, I play with it, I process it. If it's a video, I do some Photoshop and make some modification and so on. I am done. Now I need to reconstruct this signal. When I say reconstruction, means you can display it, or you can listen the voice, or you can watch the video. So that's called signal reconstruction. Depend on the content that you're processing. Technically, signal reconstruction is called interpolation. So what is the interpolation? So interpolation, okay, you sample your analog signal, you process it, and now you need to reconstruct back to the original form. So let's use the previous example. That was my sample signal. These are the value that I record. Let's say this is 1.1, this is 2.3, this is 2.2, 1.9, 1.6, and so on. I have such, values, samples basically, a vector that includes some values. These are the samples. So I need to convert this back to this original. Remember, that was the original signal. I need to reconstruct this original signal based on these samples. How do I should do that? So the simple way is to connect these dots, right? These values. So fill up the gap between these two values, basically, right? That's visually the intuitive approach to solve this problem. But how do we do that in terms of mathematically? Actually, remember, sampling was replication of this, copying this information or signal every fs. So in practice, I have a many copy of this information, and I just need one of them, which is the one at the center, the first copy. And I need to get rid of the other copies on the right and on the left side. So that's why I'm going to use a rectangular filter to get rid of the other redundant replicas. So what is the rectangular filter? As you see, is a rectangular shape. You just pass this information and you make 0 the remaining signal. So if I apply this rectangular filter, means I'm gonna multiply this signal, right, with such signal. So filtering this signal in frequency domain correspond to the discrete time into this continuous original signal. So in frequency domain, you are multiplying, you are filtering these signals. In time domain, this correspond to the filling up this gap, so that you are making this discrete time signal convert back to the original continuous time signal, as if you are connecting these discrete dots values. So this process is called interpolation. Okay, let's go to the details. The time domain interpretation for the interpolation. In frequency domain, we are multiplying the signal with the rectangular shape filter, as you see. The rectangular shape, if you apply the inverse Fourier transform, the corresponding shape is the sinc function, as you see. This function is called sinc function. The inverse Fourier transform of a rectangular filter in frequency domain correspond to the sinc function in time domain. And as you see, the sinc function has a main lobe and it has a fading side lobes. As you go to infinity and minus infinity, these side lobes fading down. Okay. that's why when you convolve, when you apply the interpolation, as if you are moving this shape over this, not this one, you are moving this shape over the samples. So that's what you are filling out the gap between two dots. Okay. Everything goes fine when you follow up the Nyquist rate. Means that your sampling frequency is greater than 2 times of the bandwidth of your signal. But if your sampling rate is smaller than the Nyquist rate, in other words, Fs is less than 2 times B, then you are in trouble. Why? What's the problem that you are creating here is, as you slide this shape over the pulse train, as you see, these side lobes, they're gonna overlap to each other. So when I say side lobes, it contains the information. So the information is actually mixing up. So when this information mix up, it's really to separate them later on when you reconstruct, when you apply the interpolation. So that's trouble, you know, you're getting in trouble. If these, you know, side lobes, this information overlap to each other, if start to mix each other, then the reconstruction of this signal back, it becomes really difficult. It becomes a tedious task. So I think you understand the problem. So if your sampling rate is less than 2 times of the bandwidth, in other words, it's less than the Nyquist rate, then the side lobes of this copy of your information, they mix to each other. So later on, because we're going to apply the rectangular filter to get rid of the other copies, then you are going to cut your information as well. In other words, you're going to miss some of your information. So what's the solution then to this problem? By the way, in the literature is called aliasing problem. So aliasing problem is one of the most important problem in the signal processing. So what's the solution for this aliasing? There are many solutions in literature, but the most popular one is to use anti-aliasing filter. So what's the anti-aliasing filter is to sacrifice the overlapping segments. So basically you're going to sacrifice the overlap, the mixed part of your information to cut hand of a body so that you can protect the whole body. Anti-aliasing filter, how it works, this solution. So before we sample a signal, we are going to pass through a sharp rectangular filter to get rid of the tail, the side lobes that I mentioned. Because these tails, remember, they were yielding to the aliasing problem. In other words, they were mixing to the next copy. So this kind of a proactive solution that before the mixing this copy, I'm going to cut these tails so that they don't mix each other. This is the simple solution strategy that this solution follow up. Of course, what's the disadvantage of this solution? You're losing some of the information on this tail as well as on the left tail. So you are sacrificing some of the information. You are losing some of your information, some of your voice, or some part of your video, or some part of your text, whatever. But it's better than phasing the aliasing. So it's much better than to create a aliasing problem. So when we before sample this signal, we're gonna pass through a sharp rectangular filter, cut these tails so that we don't create any overlapping or aliasing problem. As you see, when you cut, there's no any overlap from one copy to another copy. This way you avoid the aliasing problem using the anti-aliasing filter. So how do we explain or interpret this aliasing in time domain? So that was the sample signal, original signal. These are my sample points, right? Sample values only. When I apply the interpolation, I'm gonna fill up this gap and it is gonna look like this. So because during this sampling, we lost some information, and this because of the aliasing, we lost some of the information. They mixed to each other, and this is gonna come back like this. That was the original signal. That is the signal that I reconstruct. Of course, it looks similar a little bit, but as you see visually, you can see there are some differences, right? And these differences is because of the aliasing problem. What leads to the aliasing? Because you sample your signal smaller than the Nyquist rate. So if you sample your signal less than Nyquist rate, that's what gonna happen. That was your original signal, and that was the signal that you reconstructed. As you see, if you put them each other on top of each other, you see there are some loss of information. Okay. Any question so far about the sampling and interpolation, aliasing? Is it clear?
Yes.
Okay. So let's have a 15 minutes break and come back at 2:30. Evet arkadaşlar, merhabalar. Kaldığımız yerden devam edelim. Geliyor mu? Tamam. Okay, so in the first lecture, we went over the sampling theory. Now in this second lecture, we're gonna see the application of this sampling theory in the communication systems. So that's why we are gonna go over at basic digital data transmission. How do we get our digital signal? Is basically pass through this process to digitize a signal, starting with the coding, then A to D, analog to digital conversion, Nyquist sampling, aliasing, dynamic range, quantization noise, and compounding. So these are some process and the concept that we're gonna see the application of the sampling theory in digital communications. So what's the coding? So one of the first steps is to convert an analog signal, which can be speech, video, text, other sensor data, IoT data, such signal into a digital form. So such coding is called waveform coding. So because there are some other coding technique in digital communication systems, such as source coding, channel coding, modulation coding, and so on. So what's the source coding? It modifies an analog or digital source to make fit to the transmission. So example for this source coding can be JPEG, MPEG, other format. Channel coding, it add a redundancy bits to the signal to improve the detection and correction of the errors during the transmission over the channel. Modulation modifies a modulation symbol to overcome some error as well. So analog to digital conversion, as the name implies, we are converting an analog signal into the digital form so that we can process the signal, the samples. This is known as also PCM, which stands for pulse code modulation. So this involves the following steps, the process: regular sampling of the input signal, conversion of the sample to a number, accuracy of the A to D converter depends on the number of bits. So one of the most important parameter in the ADC devices is the number of bits that you used for the sample. For instance, for the speech, we usually use an 8-bit. For the music, high fidelity, hi-fi, 16 or 18, even sometimes 24 bits. For video, we have 3 colors, RGB. For each colors, we use 8 bits, so total is 8 times 3, 24 bits. So one of the most important parameter in ADC devices is the number of bits that you're going to use. And this number of bits, of course, it has some trade-off. When you increase this number of bits, you can increase the quality of your signal, the quality of your music or video. But this comes with the complexity. So you need to process such, quality signal with a strong, high performance, the processor, as well as you may need more memory. So the question is we can send this information from your phone, one point to another point, through the analog communication. Why do we need to convert them into digital so that we can transmit our signal or our information using the digital communication? So the question is, what's the advantage of digital communications? So when we convert a signal into the digital domain, we can make a lot of things, such as the new noise immunity. So we can mitigate some of the noise effects, such as, noise canceling, noise reduction, and so on. So viability of the regenerative repeaters, we can, repeat this signal to strengthen, the signal. And it's easy to implement with the microprocessor in digital circuitry. You can apply different coding to improve the performance of the system or the quality of your signal. Easy storage of the data. You can, store these sample values in memory more easily. And compared to the analog system, has a less cost, lower cost. So because of this reason, we prefer to convert or sample our signal so that we can convert into the digital domain. Okay, so we already discussed about this analog versus digital in one of the first lecture during the semester. Remember, there was 4 concepts: continuous time signal, discrete time signal, analog signal, digital signal. We learned all these, different types of the signal. And remember, analog was defined for all instances of the time, amplitude is continuous, and the digital signal was defined at discrete values of time, amplitude is restricted to finite set of values. For instance, this is a sync function. Okay, let's try to convert this continuous time signal or analog signal into digital signal. So we have a continuous time signal, which was this. And then I need to sample this. You guys learn what is the sampling was basically to multiply this original signal with the pulse train, right? And these are the pulse train, as you see. So after you multiply the continuous time with the pulse train, you obtain the digital signal. Sorry, the discrete time signal. Still, the amplitude can be continuous. And the next step, we are not done yet. We need to apply the quantization. We quantized this signal. What's the quantization? I'm gonna just show you guys later on. You just assign, so from the minimum to the maximum level, you set up a number of levels. And this depends on the number of bits that you use. Let's say your ADC has a 3 bits. So that means 2 to the power of 3 bits is equal to 8 levels. So I split this y-axis into 8 levels, starting from, let's say, 000, 001 up to 111. So we have 8 levels because of the 3 bits. And I'm going to assign each of these sampled value to the nearest bits. Okay. Let's say that level was 00. I'm going to assign this to 00. And that some value is close to the 001. I'm going to assign this to the 001. That's this operation is called quantization. Nyquist sampling. So so let's summarize. The ADC consists of 2 steps. The first step is the sampling. The second step is the quantization. Sampling simply is to make the time x-axis to discretize the x-axis, as you see. And the quantization is to discretize the y-axis, basically. So in the Nyquist sampling, remember, what is the goal? So the goal is to actually represent each of these dot, this sample dot, with the minimum number of bits, represent this value with the minimum number of bits. And keep in mind that to satisfy the target quality of service. In other words, with target tolerable loss of information. So that's why, again, we are going to follow the Nyquist rate. And what was the Nyquist rate? Is to sample the bandwidth. We are going to choose a sampling frequency that is greater than 2 times of the bandwidth of your signal. If you sample less than this rate, you're going to end up with the aliasing problem. And remember, what was the aliasing problem? We just went over. So let's say this is my frequency in the frequency domain. This is my original signal in time domain. After the sampling, which is less than Nyquist rate, it's gonna look like this. In frequency is gonna look like this. And after that, if you're gonna interpolate to reconstruct, and this is the aliased, because the aliasing happens. So this is the aliased output, and this is your original output. As you see, there are some differences between the aliased output, which you reconstructed, and the wanted output, which is original signal. So this is the aliasing effect. What's the aliasing effect? So I have these dots. I need to connect this dot in such a way that I can obtain this original signal. But there are many ways to connect this dot. So as you can see from here, I connected this way. This is my reconstructed signal. Okay, so it's pretty close, but as you see, there are some differences between your constructed signal and the original signal because of the aliasing effect. And we talked about aliasing, so we have the same problem in the digital communication systems such as Wi-Fi, 5G, 4G. So we have similar problem. So let's talk about some practical sampling examples. So we need to, one of the rule of thumbs, we need to filter out the baseband components above the range of interest. According to the Nyquist, is minimum 2 times, but in practice, what is suggested is to use 2.2 f max in practical filters. Let's give some, some speech telephony that is in most of your smartphone that you use to record your speech when you talk over the phone. So our speech signal is between 300 up to 3.4 kilohertz. So that's why, according to the Nyquist, the maximum frequency in this case is 3.4 kilohertz. So we need to select a sampling frequency that is 2 times of this, which is 2 times of 3.4 kilohertz is equal to 6.8 kilohertz, right? So you have to select, you must select a frequency that is greater than these values. And so in speech telephony, we usually select to be 8 kilohertz. For the CD, you guys, I don't know, have you used before? Nowadays, we are not using anymore, but we use the CD to convert analog signal information into digital and store it, right? So that we can later on play back, such as your music, your videos and images, right? Pictures. So when you burn your music or your image or pictures, videos into the CD, we apply of course, this sampling theory. For instance, in CD, let's say I'm gonna sample the music and store it into the CD. So what's the typical audio band is 15 kilohertz. So according to the Nyquist, I need to select the sampling frequency, which is 2 times of this. 2 times of 15 kilohertz is equal to 30 kilohertz. So you need to select a sampling frequency that is greater than 30 kilohertz. But because of some reason and capacity and so on that we're going to see, in the CD is the most common sampling rate is 44.1 kilohertz. Dynamic range is another important when you perform a sampling, because as you see, this is your signal, let's say, and your signal level can be up and down, depending on the signal, such as speech, video, and other sensor data. For instance, speech, sometimes, this dynamic range, it shows the minimum and maximum level of your signal that can reach. So we select a sampling, system so that you can fit into this max and minimum value, which is called dynamic range. For instance, in speech that we talk, sometimes we can talk quietly like this. And in this case, the level of your signal in terms of voltage is low. But some people, they shut up, talk, very loudly, right? In this case, your signal is gonna go up. So your smartphone or your sampling system has to, cope with this dynamic range, with this fluctuation. Otherwise, so if you don't set up your dynamic range, then your voice is gonna be cut up, and you are gonna lose some of your voice. You lose some of your information. So the dynamic range is very important in terms of sampling theory. In this case, we have a 4-bit ADC. To the power of 4 bits is 16 level, as you see, starting from 000, 001, 010. So I have about 16 level, right? Which my signal in this case can have a minimum voltage of this level and the maximum voltage from this to this point. So the ratio of the Vmax over the Vmin, it gives your dynamic range either linearly or in terms of decibel, which is the log scale. So when you design a system, this is very important to keep in mind, okay? So we already mentioned about that. When you select an A to D ADC device, you need to make sure that it can deal with the both large and small signal, this fluctuation. Of course, more bits, as I mentioned before, in terms of quality, it provides more quality, but it comes with the cost. And in terms of computation also, if you increase the number of bits of the ADC, you increase your cost as well as the complexity. But of course, this comes with the advantage of high quality signal. Okay, an n-bit converter can differentiate between to the power of n. N is the number of bits. We said in this example it was 4 to the power of 4. We have a 16 level. So L is, in this case, is 16 levels. So minimum signal variation it can detect is Vmax over L, known as the quantization step size. And there's some quantization noise problem, as you see from here, because this is my, value actually. Let's say this is, I'm just giving an example, 5.3, and this level is 6, this level is 5. So am I gonna assign this 5.3 to the 5 or 6? Logically, you need to assign a value to the nearest level, which is the 5 in this case. But when you assign this, you are actually introducing some quantization noise. In other words, you are losing some information because there's no exactly 5.3 level. So when you assign to this 5, you lose this information, which we call quantization noise. So this quantization noise is a very important source of the noise. So you have to be careful about this quantization noise when you select the, as you see, this is also related to the number of bits. Because the number of bits, it shows you the, it determines the levels, the signal levels that you're gonna use. In this case, it's 16. When you increase to the 32, what's gonna happen? You're gonna have more quality because, right? But this comes with the cost and the complexity, as I said. So you have to optimize your dynamic range, your quantization noise, and all these different parameters. Okay, so some real problem application of the sampling theory in our daily life. Speech telephony. Speech telephony is the system that we use when we talk over the phone. So it gets your speech when you talk to your mother or father. Then it converts into the samples and it's processed. And after processing, it's sent over the link, which can be Wi-Fi, 3G, 4G, whatever link that you are using, or Ethernet. And then on the other hand, your mother, father receive your voice, speech through the whatever Wi-Fi, 3G, or Ethernet fiber optics, and it reconstruct from the samples that you sent. And so by applying the interpolation that we just learned, and then after the interpolation, it reconstructs the original signal, and then you listen, or he or she listen from the speaker. So when we send a speech signal, the following are the common parameters that we use. First of all, the human speech spectrum is from 300 to 3.4 kilohertz. So our speech has this specific spectrum. In other words, our human speech is between these two frequencies. So the maximum frequency is 3400 hertz. So we apply, remember, in order to mitigate the aliasing problem, we applied anti-aliasing filter, which we filter at 4 kilohertz to cut these tails. And then we apply this, first of all, in the first step, we apply the anti-aliasing filter to avoid the aliasing problem. After that, now we are gonna start to sample, but at which rate? Of course, in this case, is 3400 hertz. So according to the Nyquist, we sample 2 times minimum which is going to be 6.8 kilohertz. That is minimum, but we selected to be 8 kilohertz. And then we apply other kind of technique, 8-bit ALO. And then, as you see, it's going to be 8 times 8. The data rate is going to be 64 kilobits per second. So every second we are going to transmit 64 kilobit, a bit stream, basically. Okay. So we show one of the main application of this sampling theory, which is PCM. And PCM was pulse code modulation. In other words, is the process of converting analog signal into the digital signal. And the PCM, remember guys, it consists of 2 steps. The first step is the sampling. The second one is the quantization. Sampling, we do discretization in time in x-axis, and the quantization, we discretize the signal at y-axis. And of course, in the sampling, we have the aliasing problem. So in the quantization, we have a quantization noise. And the quantization accuracy is determined by the number of bits that you used in the ADC. So you have to be careful when you select the ADC, and specifically the number of bits that you're going to use. And the quantization noise is one of the main error source that affect the quality of your signal. This can be the video, it can be music or speech, voice, data. So, and the signal to noise ratio after the quantization corresponding to uniform and non-uniform quantization. So these are the main things when you convert a signal from analog into the digital signal, considering the sampling theory. Okay, that's it for today. Any question about the application of sampling theory? No? Okay, guys. That's all for today, and I'll see you next week.
All right. Have a good day, sir.
You too. Bye.